Yeah, Dr. Gar, can you hear us?
Yes, I can hear you.
Okay, perfect. Okay, so hello everyone. My name is Matthew Dowie, and I'm going to be presenting recursive language models. This paper was done by a PhD student at MIT, and it was released the beginning of this month. And the main reason why this paper at least caught my attention was due more to the fact that the problem that it was solving, and also the methodology of going about solving this problem. The main problem that was shown was that was particularly context wrought and performance degradation. Context wrought, simply, Anthropic's definition is that the more input tokens are essentially inputted into a model compared to how large the context window is, the actual performance and quality of the answers of the model will begin to decrease. Still, if you are a individual or just if you are just a simple practitioner of, let's say, like models like ChatGPT or Gemini or Grok, you can find that context fraud is simply that the more you ask questions to the same LLM model or the same LLM model in memory, you will find that the LLM over time begins to give you
Mhm.
less quality answers. And not just less quality answers. It also can have issues where it actually hallucinates your answers, or it might just forget altogether it might forget altogether the context of answers might have done that were maybe older than about 24, 48 hours. And this can cause I think the main problem is that this can actually cause not just it causes not just issues due to how large context limits are, but it causes issues due to the fact that we see models are constantly being improved with not just how they're trained, but also they're improved with the actual capacity of information they're able to use in their working memory. If
Mhm.
if they if but even if their context expanded, if the quality of their responses decrease relative to that irrationally relative to the context being expanded, then
Mhm.
it is quite a significant trade-off. And personally, I would not say that the trade-off is very viable in being used in at least industry, or being continued to be used in research fields where you want to maybe do large scale model inference or large scale model inferring, because technically you're only really training or really only understanding your context and you're having your experiments in a short form of the model's capabilities. It's not really being used to the extent of the model capabilities. And recursive learning models are essentially ways to combat this. And here's a graph that essentially shows how context rod is in the graph of different models. As we see, starting at a number of tokens where you have, let's say, one query, and we could say one query is about, I don't know, one query would be about 800 to 1,000 tokens. We can see that the accuracy in the beginning with these models is relatively high. And this is how it should be. It should be high. But what we expect is that but like, the thing we should expect is that over time the quality of the context should of course decrease, but there shouldn't be a large decrease as we see here. As we
Mhm.
see OpenAI and Gemini, the decrease goes down swiftly at about 2,000, the input length of 2,000 tokens. It rises back up, and then it goes back, and then it begins to go back down. Claude, we see here that it has a bit of a higher, more accuracy compared to the input number length, but up to a certain point, it completely crashes. And to reiterate, recursive language models are merely a method to be able to work around these issues, and it was created as a way to combat this. Oh, such random curves. Like, oh, So these curves are not exact representations. I merely just got this graph off of Google to essentially show you what it would look like. So of course there are like experiments that show the experiments are shown in more of a or I have actually a graph later showing input accuracy to the input length, the number of tokens later on when I compare the RLM to actual frontier LLM models. But this is merely to basically give a general representation for minimal understanding. So the solution is instead that RLMs use is instead of actually using the prompt query or using the prompt or the context in actual models working memory, we actually keep this as an external piece of data. This sounds very similar to RAG in the sense that we are going to have an outside we're going to have an outside piece of information, and instead of the model actually having to ingest that information, it's converted to embeddings and such. But the main different thing about this is that the type of way it's being used as external as data management is it's actually being used as a string, a variable, or an environmental variable that you would find in your code inside a Python environment. And this Python environment is the standard Python read, evaluate, print, and loop environment. And because it is treated as a variable, the language model is now able to manipulate and do other things with the prompt compared to the amount of context it has, and it is allowed to run scripts and basically allowed to run scripts and different Python commands to essentially manipulate the code, to essentially manipulate the actual prompt or context to be able to get a lot more accurate answers. Here's a simple example of how this is working. So you have a query, and the query goes to the language model. The RLM could be imagined as not essentially the language model itself. However, it could be imagined as a wrapper around the language model, which actually allows the language model to communicate with the environments. And the environment in this case, as I said previously, is a Python read, evaluate, print, loop environments. It's a Python standard environment which contains the oh, can I click yeah, slideshow. Yeah. So it's probably a bit small, I think, maybe from the screen. After when I ask a question, I can expand it and go into greater detail. But as you see, simply the query is being queried into the language model. The context is within the with its context is a data source within the environment. It could be any source of text. Usually the best way to do something like this, I'd say, is using a text file from my personal understanding. But the environment that and but now the LLM now that it is within an environments, you are able to make different calls which can allow you to do one of two things. The first thing that is able to do a call is that the environment is able to call another LLM,
Hmm.
and which actually coins the part of it being recursive. In computer science, something that is recursive is merely a program that has a subcall of itself. The recursiveness in this case is that the language model within the environment can now call another language model to basically reiterate this entire process, and that is mainly the beauty of RLMs. It allows LM to break up the prompts that is now a string, and allows the LM to basically do different data manipulation operations to turn that string into chunks of different characters, and actually now use Linux commands to now manipulate the context to basically grab different parts of the context to see if it answers the question, and basically after it does that enough times, it aggregates the information and it brings it back to get you to your final response. As you see here, you have the environments. It has a subquery, which is just a chunked part of the original query. It chunks a part of the context, and then it could pass to another language model, and you have a sub response from that. And for this, this part is shown as a depth one. As you can imagine, recursiveness being like a tree. You have one branch, and if one branch is not enough to complete solve the problem, you can pull it to another branch, and that is merely what this second part is, which the subcontext two, subquery two, and the subresponse two. But as you see, this is different because it's calling a new environmental, and it's calling a new environment, unlike how this part merely just uses a single subcall, or I'm sorry, it uses no subcalls. This is more what it will, yeah. What would be the base case for recursion, and what will the second depth move on recursion? Let me see the question in the chat. Chat. What will the base case of the recursion, and will the depth of the second depth of one same as first call? Okay. So going back to the previous slide, the base case. So the base case of the recursion, from what I'm actually aware, is that the experimentation they did, it was strictly trying to more do more limiting of the time and not actually work towards finding an effective answer. So if I'm correct, the base case in this case would merely be a I'm trying to remember how they classified an answer as being proper to basically going back to the original LM, or is it's taking the information back to the original LM. But if I recall correctly, the base case is merely a single call. So after a single call, that is what would happen. And then will the second depth recursion be the same as the first call? Yes. So later in the presentation, I will show the experiments that they did. And an experiment that they did is basically actually using an RLM with no subcalls, which would be the part on the left, and using an RLM with any amount of subcalls, which would be the one on the right. And the way that you have multiple subcalls is by continuously allowing a new language model to create a new environment to act on to the same parts to the same basically chunked up context that you could have done from the first environment. And yeah, does that
So
answer?
Matthew,
Yeah.
tell me this thing. The language model, what's the size that they are considered for the depth zero?
The size?
Yeah, the what is it? Is it a small version of a language model, or they consider like 70 billion, or such a high like what's the size for the language model, and what is the type? Is it like a code generating model, or are they looking for any multimodal or text-based language models as well?
Okay. So this actually gets into the limitations of what RLMs are able to do.
Okay.
Because you could in the same way that you cannot expect let's say you cannot expect Gemini or not Gemini GPT 2.5 to
Mm-hmm.
have great coding capabilities.
Mm-hmm.
The RLM paper, they only do the experimentation on, I think it was Queen Coder 240 billion parameters, and I think it was GPT 5.2. So you have to use LLMs that have coding capabilities, so they have the ability to actually work with and have the ability to work with
Mm-hmm.
efficiently with the environments. And so yeah, so it was particularly done on frontier models. So models that like not it's
Okay.
not yeah, models that had come out like in the past year. So it has to be a type of coding model, or it just won't be able to communicate with the environment effectively. And that was mentioned in the paper.
I think I can provide a bit of clarity over here.
Mhm.
So, Dr. Go, it is not, they are not different language models. It's like once given a query, the original query, the language model itself generates a subquery and gives a subcontext to itself, and it forgets about the previous thing.
Oh no, no,
Now,
no.
whatever response it generates, it adds to the original environment.
Okay.
So it's like how we do it in the RAG setting. It's
But it's
they are
not
just
memorize, so it's not memoization. So which is like I have a small memory block of understanding what context was given to me, and I'm holding on to that context while I'm also generating subquery and subcontext.
No. You are letting go
No.
of that original whatever you had context. You're
Okay.
not just working with the newer ones, like how we used to do in, how we have been doing in RAG and stuff.
Okay.
They have just duplicated it.
And also, yeah, I think it's a little clarification. So in all of the defs or in all of the subcalls of from the environments, the language model is not actually generating more information upon itself. Each of the subcalls are calling an entirely clean
Mm-hmm.
LLM. So yeah, so it has essentially no working memory. It only has the subquery and subcontext. It has no information that the original language model has, except for the one that was
Okay.
given. Yeah. So it differs a little in that sense where your the output context is not increased.
Mm-hmm.
Only it only increases when all the information is aggregated all together. But that but in the case of how it was originally the information is not usually aggregated, and with the information that is aggregated, it's usually a summarization, and the summarization can be a bit incorrect, or it could have some hallucinations. In this case, because it is going into in a clean language model, you will not run into those same types of errors. But yeah, so a more deep dive into what the actual environment looks like.
Mm-hmm.
So we have the RLM wrapper, and this is a def 0. We see, okay, so we have our query, which we have our prompt, and then we have the output, and this output takes to this part of the code. This merely says that the sub LLM will handle X amount of characters. In this case, the amount of characters is from about half a million characters
Mm-hmm.
to 1 million characters. From there, it takes the query, and it uses that query to then actually call a new LLM, and it only takes the first half plus the query, and it
Mm-hmm.
and it basically use that information to now tell the LLM, find that information, and after it's done, it will pull that information back. So, and as you see, here's that input. The output that it shows is the output, and
Mm-hmm.
that output is shown as one. That output is shown as only one call. You can have up to n calls based on how large the context is, and because and be and because you are splitting the context by n amounts, you can get up to n clean answers. Once aggregated, the quality of the answer does not run into the original context, the context route, and also the quality in itself is much greater because you are using a fresh LLM call in each instance. So the architecture is, as mentioned, you are using an LLM within a Python read evaluation print loop environment with the prompt and context being stored as a variable. And below are some commands that the LLM will essentially use, or some scripts that essentially uses to be able to manipulate and understand, be able to understand the information that is being passed in. So what you're able to do is things like peeking. All peeking does is essentially takes part of the context. It takes takes part of the query, and it's okay. Based on this context, is that query in this context? If it is, then we have a match, and then we're able to pass that information. We're able to hold that information until it needs to be passed back into the original language model. Also, recursion. If an LLM finds that it is not able to answer a single question by itself, or a question goes past X amount of characters, then an LLM is able to now call itself again to be able to have a fresh, clean working memory, and it basically uses that again, and that fresh LLM could do the same peeking, recursion, and then going to the last part, divide and conquer, which simply is that the model actually basically takes that problem, decomposes it into subproblems before aggregating all those subproblems together into one final output. And you are able to do also other Linux commands such as grep. Grep is a command on Linux that actually allows you to go through a large file and to basically find certain words and modulate, and basically find certain words or certain phrases and modulate them together over multiple files. And yeah, here's some results. So Oolong is a database, is not a database, is a data set that was created particularly for long input tokens as context, and it basically wanted to see how an LLM does, particularly faster LLMs, based on having a large context. How properly can they how accurate could the answers they get be? So the baseline, it used this case of GPT-5, and GPT-5 received, as you can see, the chart is relatively self-explanatory, but the greatest thing is that here is that compared to React GPT-5 with BM 25,
Mm-hmm.
you are able to get up to a 30% increase in accuracy.
Mm-hmm.
And that is for the that is for GPT-5 with subcalls. For the GPT-5 without subcalls, then all that merely means is that you're able to put the variable into a you're able to put the variable into an environment, but you don't have the ability to actually now recursively call new LLMs with fresh context inputs and fresh complex output and fresh working memory. You're only able to use that original environment you had, and you're not able to have any LLM calls onto it. The graph on the right actually now shows the cost per query per token. And as you see, GPT-5, it did have relatively cheap cost, but compared to the accuracy and compared to the cost for the RLMs and RLMs without subcalls, you can see that the accuracy that you see
Doubles.
it actually doubles compared to the cost, which in most industry cases, and I think actually in a researcher's case, this scale is not this gain is not a waste of compute power,
Mm-hmm.
particularly to how much of an improvement it is. And if people are actively working with large context windows, uh, this they most likely already have the compute power to be able to work with this. So this actual incremental cost it should not really be should not be really a main factor of limitation for their experiments. So this next graph actually shows with previously we had this shown with 132 tokens being input into a model. This is now 263 tokens being input into a model. And as we see, the baseline GPT-5 has about 34.2% compared to the RLMs, which have here about a 15% increase with 51.1% and 41% compared to the average cost, which we see again is relative to how much GPT-5 costs, and GPT-5 for the offer mini for the RLM actually costs less for per query per token.
Mm-hmm.
So these plots are now the correct answer rates compared to how much information was actually inputted into inputted as into the working memory. As we see here, we have GPT-5, which was the baseline used. At about 50 documents chunked, the correct answer percentage rate fell to about 43%. At about 100 documents inputted, the correct answer rate fell to about 10%. And at about 1,000 documents inputted, the correct answer rate fell about to 0%. For RLM with GPT-5, the answer at 10 papers it was 100%. At 50 papers it was about 93%. At 100 papers it was about 93%, and about 1,000 papers it was 100%. Personally looking at the graph myself, when I had personally saw it, I was a bit, I guess to say, I was a bit confused on how the correct answer rate decreases and then has a sudden increase back to 100% at 1,000 documents, which did not seem like that was something that was likely. Maybe it was due to how they experiment on this. They did provide the experiments they did in the ballot and paper. I did not have the chance to actually go through it myself, but merely looking at the graph, this just seems like it's an unlikely scenario. However, the GPT-5 without subcalls seems like it's a much more seems like it's a much more valid and accurate representation of what would happen. And still, the performance is still a great improvement compared to React with using GPT-5. So regardless, that it still shows significant improvement. On the right, it shows the average cost per query per content document, and as we see, we have GPT-5 it costs about roughly 5 cents at about 10 documents. At about 100 documents, it costs about 25 cents. The RLM with using GPT-5 goes from about 15 cents to now 55 cents or 60 cents at 100 documents, up to upwards of $1 at 8,000 documents. And this is the average API cost per query. So all this means is that every time every time you answer a question, that's how much it costs overall. That is not how much is it costing per token. That's how much it's costing for the entire answer. But as we can see that React with GPT-5, the price became upwards of $2 and about 10 cents at 1,000 documents, which I don't know which lab or which research group, unless they have lots and lots of funding, will be able to even afford doing experiments to something of this scale. So back to some limitations. All the experiments done on these models were completely dependent on frontier models. This merely means models that were done in the last year, and 90% of the experiments were done on models like that. So and when I say frontier models, people usually think of frontier models being about GPT-3 and above. No, the tests were done on GPT-5, 5.2, GPT Queen, Queen, I think it was 240 billion, Queen Coder. It was done on React with GPT-5, which and all React is just basically a different method, it's basically, I think it's a data set trained, if I'm recall correctly, but it is still a relatively new method. So yeah, all the experiments are done on these newer models, and this actually leads to the next point. They're done on the newer models because of the coding capabilities. Most past models, they might have relatively strong simple coding capabilities, but in the sense of their experiments, they weren't actually able to create a proper experimentation and proper actual visualization of what it looks like. At least back when I was in high school, in our high school, the best GPT that we had for ChatGPT was GPT-4, and it seemed that it was relatively accurate for simple programming scripts for Python. So I'm not sure exactly why they stuck to using GPT 5.2. Maybe because of the reasoning aspect that you would need when you are doing these type of problems. But yeah, those are two limitations, and then the third limitation was the lack of asynchronicity. All that essentially means is that all the subcalls that were happening within those subcalls that were happening within the actual runtime of basically going from the query to the final output. All those subcalls happen in a sequential time. The experimentation was not done in a way where that all the models had subcalls basically parallel to each other. This actually caused some of the queries and some of the answers to actually have run times of about 5 minutes, 5 to 6 minutes, and because you'll be calling a new LLM per subcall, these can range from about 3 seconds to 5 minutes each. I think the greatest they came upon was about 5 minutes for one subcall, and that in itself is a way of improving the actual usage and its actual usage in more industry like terms, or maybe even research. But I think one thing that I forgot to mention was, I'm trying to remember. Yes, one thing I forgot to mention. I handled it a little bit in the beginning of the presentation, but this research was particularly done as more as a reveal for a new methodology or new type of research on these type of language models in a way that in a way where that it wasn't that the necessary coding and necessarily optimization was not as effective as it can be. And this is shown with the lack of the lack of asynchronometry, and this is also shown with other things that they talk about in the paper. And all that really goes to show is that this this type of models are not efficient yet. They had their use, and they can grow to become more efficient. But currently the code and like the models that we're using in this paper and how the scripts are called and such are not very efficient. It is merely to show that and it is a bit of a disclaimer. It is merely to show that there is a new technology with these types of models. But however, if you want them to be efficient, you're going to have to tune them and work on them yourselves until they actually have usages in things like industry or the actual research field. So some future. So a future work that was talked about was doing some native training. And this essentially is basically instead of having to, and I can pull it up if necessary, if you guys want to see it, the actual length of the prompts that were given to make the LLMs act like RLMs. Instead of having to do those prompting, you can actually train models to actually have the ability to be able to reason recursively and manage their own memory. This is talked about in the paper, and also future work also can also be making them more efficient, like I talked about in the previous slide. But things like this are relatively simple things that can be done for to make it more future-proof and more viable for researchers to use in the future. Here's the acknowledgement and open to any questions. But I want in case that I want to go over something that I did. I want to look at something that I did. It was particularly comparing chain of thought and comparing this methodology because particularly because I know that Reza looked a lot about tree of thought and chain of thought, and so I want to think how particularly are these different. And so I don't have the table created of how specifically they're different, but more or less more or less for RLMs when the actual LLM interacts with the Python environment, the context and query and prompt are all taken in as variables, and particularly string variables. And once they're taken as string variables, you're able to do programmatic commands to be able to manipulate, find, and respond with the information that is found. For things like RAG actually creates embeddings of documents, and these embeddings and from these embeddings you will use an encoder, and you would essentially want to find the similarities between the prompt between the queries and the actual chunks of content that you have, and that's how you get your answer for chain of thoughts. Chain of thought is actually more where is actually more where you are actually you're taking the inputs, and you are doing a wide scale reasoning over that input and query over the content you have to be able to generate a better answer. So it's merely the LLM basically asking itself questions. The problem in chain of thoughts is that you only have the amount of space you have per output context. The actual reasoning that happens within the LLM is being done in the LLM's working memory. All that essentially means is that all that information is happening under the hood, but it's all of that happening within the LLM. So the second you actually run out of the context output for the LLM, the reasoning can abruptly stop, or it can just chemically give an incorrect answer. And we have already seen in the previous charts, and I'm sure you guys have seen in your own experiments, when you reach closer to the output limit, the answers begin to degrade severely. So these are the three different methodologies, and these are like at least from what I know, like was being used widely in the lab. Like I think Yash does stuff with RAG and such, and Reza did stuff with with chain of thought. So that is at least how these differ, or this is how these actually not just differ, but how they might be similar in how they work together. And I don't see why in the future you would not be able to combine these different methodologies to get more quality outputs. But yeah, that is more just the ending thought, and that's the end of my slides. But if any questions, I would appreciate it, you guys ask. And yeah, any questions you guys want to say? Yes, Akshan, you have a question?
So I have a question. So this is so every recursive call is making the response better.
Yes.
Okay. Okay. So if we get into like first recursive call, this will make the response more better.
So so I think I've seen what you think. Let me go back to the. I think I've seen what you're more saying. So this actually
Yes,
works
sir.
to this part of the slide. This so better on this slide. So the count. If you have a textbook and
Mhm.
I'll make this example similar to, let's say, what the work Yash did. So Yash did work with a Bloomberg with Bloom I think it was Bloomberg, and so imagine you had a corpus of information from a Bloomberg textbook, and you have all that information all into a one text file, and that being X amount of size. Let's say it is 100 megabytes. Essentially, you pass in the query, and the context you have is essentially is all the context you have is essentially those documents, and those documents are actually chunked up into, as you have first half and second half. Those documents are chunked up, and it can be taken to n halves. And once you have n halves, it takes the query, and it takes the first half. It takes the first half, and it combines that, and uses that into an LLM call, and that is one recursive LLM call. It does, and then it does it again. Your second half, your third, your fourth, your fifth, your sixth, your
I
seventh,
see.
your eighth, and so on.
Mm-hmm.
Mhm.
Once you have all the information, and once the information that actually uses that entire query, it aggregates it together, and it summarizes it and such, and I use that information, and as you see at the bottom, you verify it. You actually have a verifier to actually make sure that all the information is basically proper and such, with the prompting you do, or not the scripts. And
Mm-hmm.
with that all that aggregated information, it combines into your one output.
Yes.
It is not necessarily that the one it is not necessarily that you do the call and it makes it better. It does not actually affect the original query until you actually find your answer, or until you go through all the LLM calls. So until that happened, the original output is not generated. The original output is only generated after you have all your after you have all of the queries done from all of the LLM calls. Once you have that information, then you actually go and you say, okay, the answer is created from all that information. Does that make sense? Or does that answer
Mhm.
your question?
Yeah.
Okay, perfect.
So Matthew,
Yeah.
are these functions that the model is creating? Is the model generating those functions, or they are given to the model?
So these functions are not being generated by the model. These functions so okay, so
So it
the
actually
overlaying
takes
information.
it actually takes me back to the
Yeah.
Karpathi's YouTube videos, which mentioned that the only way to ensure that the model semantically understands your query
Hmm.
is to enable the model to first create a Python code, Java code, C++, or C code
Hmm.
of the query that the user has given to him,
Yeah.
given to the model.
Yeah. So I so I so I so I so I think that there are instructions onto how to shape the actual code.
Mm-hmm.
So of course do peeking, do the grep,
Okay.
do the recursion and such. So I'd say that it has the outline to be able it has
Okay.
the outline to create the code. to then answer the questions. But it is not like deciding, okay, do this, do that, do this, do that.
Okay.
It is more in the prompt. It's given instructions
So it's
on
all
some
more
like
like a
things to do.
sequential that do this, and this, and so on and so forth.
Yeah, exactly. So
I see.
if it's
Okay.
this, decide to do this. If it's this, decide to do this, and build off from that. The code itself, the and from that the element actually generates code to actually do that, but
Mm-hmm.
it doesn't know to do that unless you have the prompt. And
Yeah.
that's actually why I think I talked about closer to the end, like the future work. Instead of having to prompt the LLM to actually do that, you can actually train it to actually act like that instead.
Mm-hmm.
Any more questions?
Interesting.
Yeah.
Interesting. Sarvesh, do you think that this would benefit from the line of work that you have been exploring in thought of search and auto toss? And Saksham, you can also pitch in.
I think it will take time, like to, I mean, for every response, like there is like a, a lot of computation. I mean, recursive calls will take a lot of time.
Yeah, I know, but let's say I have a sort of a memory, a look ahead, and a look back function, for example, on what I have identified as an important at the first, and what are my next steps, and I'm considering those as important. Then I'm checking whether it aligns with the previous information that I have already parsed, I would say, compared to what I'm looking ahead. So if I have a look back and a look ahead function in my model, right? Think of it as like a bidirectional linked list, right?
So,
I might
uh,
have a better way of doing it.
so I think the point of toss or auto toss is that to lift the computational load from an LLM to a classical search algorithms.
Uh-huh.
In case if we want to pursue this look back algorithm, we don't really have to do this. We can just do alpha beta pruning,
Yeah.
traditional AI method, which would be much more suitable to what auto toss is rather than this method.
So would this line of like angle, so would this data set be a good use case to the approaches that you guys are building? The oolong data set.
I do not like. I can't answer this
Okay,
question
so
unless I
have a
know
look at
about
it.
the.
And another thing that I've been exploring recently is Olang data set. It's a G at the end. Yeah. And another interesting thing that I was wondering that this paper would be including was a method called pipe rag, which is one of the fastest. Like they say it that it's going to be the fastest rag approach there, and because one of the authors was an inventor of pipe rag. So I thought like PipeRag would have been a more comparative baseline to recursive language model, because one of the approach that they are evaluating is also similar to what the RAG would do. Uh, One another point that I wanted to discuss in this along this line, and that's why this paper was something that was on my reading list, but I haven't read it, and glad that Matthew found it. Yeah, so there is this company called Utori, and what they are looking at is agents for marketplaces, right? And the second angle that I was reading, I was thinking that this work is important is because listening to a lot of people in the Bay Area and in the Silicon Valley side, what I found is that they are more interested in using LLMs and building new things, or enhancing the capabilities of LLM to do something miraculous rather than reinventing the wheel. So this is one angle I would say where you are not reinventing the wheel, but you are just extending their capabilities to do something, right? So that is another angle that some we can pursue going forward as well, because that is something interesting in my understanding, because LM scaffolding have been something that people are exploring, and probably Shashwati knows that we have this interaction with someone in Microsoft who told that we are more investing in LLM scaffolding approaches compared to reinventing the wheel. Yesterday also I was having a conversation with a company, and they said that they are interested in, let's say, taking a llama model 70 billion, try to reduce it, try to make it fast, not reduce it, make it fast on the GPUs, so that people can easily exercise 70 billion without sacrificing the expressiveness of the model. So they are not saying that we are not interested in going to 8 billion, but if 70 billion is giving us spectacular performance, and the hurdle that we have is that it is difficult to load and execute, can we do something better in that space? Right. So those areas that people started looking at. Another one was this tiny recursive network by Samsung, and then there is hierarchical recursive models, HRMs, recurrent models or recursive models. I forgot the name of it, and this is from one startup in Sapient in Singapore. So I think this angle of the recursive models have a lot of recently getting a lot of traction in various applications area as well. So in the context of Utori, right, which actually motivated me to look at recursive language model was they wanted to say they want to develop an agent that says that here is the here is a user query that says that I want to plan my trip for this conference that is happening, XYZ conference happening in Padua in Italy. Uh, can you plan my itinerary? Now, when you say plan my itinerary, they want to do the planning, they want to do the booking, they want to find the best cost, best package for you, even including the Uber cost, and finally they just give you that this is the final cost. You just need to hit the button pay, right? And they are doing all of those searching over the Expedia, Kayak, and various agencies and things, and then bringing those and that's just more of like an agents for the marketplaces. And for them, they are also looking at recursive and recursive models and breaking down the major query of the user into sub query so that your planning is smooth. So those are like some of the use cases that actually got me look into the Google search, and then I accidentally found this paper that I was wondering that I should be reading it, and glad to have Matthew take the initiative and present it. Okay, with this, any other questions, guys?